All right, so today we're going to talk about limits and limit notation. We've talked about limits some, but we didn't really use the exact terminology and the exact limit notation. So we're going to start with this warm-up, and I'll show you what we already know. It's a warm-up, so it's something we've already done. It says give the end behavior. So we've been talking about end behavior since like August, all right? And we did it with a bunch of different functions along the way. Looks something like this. As x approaches infinity, okay, so as x gets bigger and bigger and bigger, f of x approaches what? Negative infinity. Okay, and then as x approaches negative infinity, for this one, what does f of x approach? Infinity. Okay, good. All right, so that's end behavior, and one of the things that tripped some of y'all up at the beginning with end behavior is you were concerned about what was going on in the middle. And I told you, we don't care about middle behavior right now. We're talking about what happens way out at the ends, at infinity and negative infinity. So when we talk about limits, right, we are able to talk about the middle behavior a little bit more. We don't call it middle behavior, but we're able to look at stuff other than just the ends. So let's talk about what a limit is. A limit is the concept of a function approaching that word is very important, approaching a certain value. So we don't care if we actually even get there. It's about approaching that value. Just even with infinity, am I ever going to actually get to infinity? No, but I'm approaching infinity, right? So we're going to start by taking our end behavior notation and changing it into specific actual limit notation, which would look like this. So it says, given the function f of x, the limit L of f of x as x approaches c, all right, so f of x is our function, the limit is L, x is approaching some value c, is written like this. This is a lowercase lim. And underneath that we'll have x approaches c. So that you read that, the limit as x approaches c. So the limit as x approaches c of f of x equals L. So L is just the limit, whatever it is. So we're going to write the end behavior of 2 and 3 in that form. We're going to say the same thing we did with, as x approaches, whatever. We're just going to write it differently. So what we would say on this before, it was as x approaches infinity, f of x approaches negative infinity, right? Instead, we're going to say the limit as x approaches infinity of f of x, whatever this function is, equals, well, as x approaches infinity, f of x approaches negative infinity. And then going the other way, the limit as x approaches negative infinity of whatever the function is equals also negative infinity for this one. So we're saying the same thing, the format's just a little bit different. Okay? Makes sense? You understand how to read it and what it's saying? All right, so let's look at number 3. Number 3 is an exponential. So I'm telling you that so that we know for sure that this is an asymptote and we're not guessing. So I would say here is still in behavior, so it's still the limit as x approaches infinity of f of x, whatever that function is. Well, as x approaches infinity, what does f of x approach? Negative 4. Good. And then the limit as x approaches negative infinity of f of x. So as x approaches negative infinity, what does f of x approach? Infinity. Okay? All right, so that's what happens when we are approaching infinities, either positive infinity or negative infinity. So then it says, what if c is a certain value? So instead of saying x is approaching negative infinity, we say x is approaching 5 or whatever. That's more that middle behavior. If c is a certain value, then the limit is the value in which x is approaching from either side of c. So we have to come in from the left and the right and see what we're approaching. It's important to understand that a limit is not what happens at C. We don't care what happens at C. We don't care if we even ever get to C. It's about what's happening when we're approaching C. Okay, rather what is happening to the function near or close to C, like in its little neighborhood. So I'm going to show you a 4-minute video that kind of explains that a little bit more, and then we will continue on.
In a general sense, limits allow us to determine what value a function is approaching when we use a particular input. Not necessarily what the function gives us as an output, but rather what value it's getting arbitrarily close to. Let's explain limits using an analogy. Suppose you are watching TV and start getting a massive craving for pizza. Fortunately, you just happen to have some leftover pizza in the kitchen. So you get up from the couch and start heading towards the fridge. In this instance, if someone were to describe where you are going, they would say you are approaching the fridge. They would be confident in their description because as you keep walking, you are getting closer and closer to where the fridge is located. This example is the same thing we want to do with functions. When we take the limit of a function, we are describing where they are going. Let's see an example of this with the function 3x squared minus 1. For this function, I'm really curious what value the function is approaching as I use x values close to the number 2. Let's see this by using some inputs like 1.9, 1.99, and 1.999. When I use these, I get values such as 9.83, 10.8803, and 10.988003. From these values, it appears that the function is approaching 11. So we say that the limit of the function as x approaches 2 is 11. Remember, what I'm really saying here is that we can get arbitrarily close to the number 11. I just have to pick values that are sufficiently close to 2 in order to do it. Now at this point you might be thinking, that's fantastic, but couldn't you have also found the limit simply by plugging 2 into the function? Wouldn't that also give you 11? In this instance, the answer is yes. But the focus with the limit should be on what value it's approaching, and there are some functions where you simply can't plug in a number to find the limit. In other words, they are not always the same. Let's cover this by going back to our pizza analogy. Like before, you've been struck with a craving for pizza. So you are headed towards the fridge for a quick snack. Now, in one scenario, the fridge is there, loaded with pizza, and you can easily satisfy your craving for pepperoni. But in an alternate scenario, the fridge is gone, possibly stolen by pizza-craving ninjas, and you are left empty-handed. Even though both of these situations are completely different, your behavior leading up to them is exactly the same. In either case, you are still approaching the fridge. This is the key difference with limits. They are used to describe what value a function is approaching. They are not used to describe the value the function actually reaches. Let's see how this works with yet another function. Let's go ahead and use x squared minus 4 all divided by x minus 2. Like before, we are interested in what value the function approaches as we use x values close to 2. Let's go ahead and choose some inputs like 1.9, 1.99, and 1.999. When we use these, we get values of 3.9, 3.99, and 3.999. From these, it appears that the function is approaching 4. So again, we say that the limit of the function as x approaches 2 is 4. If you try and find this value by instead plugging in 2, something strange happens. When you plug 2 into the function, you get 0 divided by 0. This shows that the function doesn't actually ever get to 4. In fact, a quick look at the graph shows a hole right where 4 is. Despite the hole, the behavior of the function leading up to it is the same. Since the behavior is the same, we still say that the limit of the function as x approaches 2 is 4, even though it never actually gets there. Hopefully both of these examples really highlight how limits focus on the behavior of a function, what they get arbitrarily close to. One thing we still have left to cover is what it exactly means when we say that a function gets arbitrarily close to a value. But don't worry, we'll be able to tackle that tricky problem in the next video when we introduce epsilon and delta. Thanks for watching.
Okay, so the whole point of all that was we don't care what we actually get to, whether we get there or not. It's what you're approaching. Your refrigerator might have disappeared, but you were still heading there, right? So let's look at this example. So we need to be able to figure out limits from tables, from graphs, and from just the function itself. We're going to look at tables and graphs today, mostly just tables, though. Yeah. Looks like I lost my piece of paper that has my numbers on it. All right, so if I want to estimate the limit as x approaches 2 of this function here. So I'm going to pick some numbers that are a little less than 2 and a little tiny bit greater than 2. In the video, he only did like a little bit less, but you really have to go from both directions. So if we were to substitute in 1.997, you would get negative 0.752, and then we'd get negative 0.751, and then negative 0.751. Substitute in 2.001, we'd have negative 0.750, negative 0.749, and negative 0.749. Okay, so if I'm trying to estimate from a table the limit as x approaches 2, I'm approaching from less than 2 and approaching this way from greater than 2. What do you think would go right here? What would make sense? Yep, so just negative 0.75. All right, everybody good with that? All right, let's look at some graphs. So we're going to estimate each limit using a table or a graph, and we're going to look at the graphs more than anything. So the limit as x approaches 4 of 3x minus 2. Oh, this is the graph of the first one that we did, where you can see that the table was approaching 0.75. They just had like the bigger numbers on there I was going to show you. All right, so here's the function 3x minus 2, which is your number 4. And I want to estimate what happens as x approaches 4. So here's 4. As x is approaching 4, you can see, but no matter what I do, my hand's on the way. In Desmos, you can click and drag. So it's a little bit greater than 4. It's a little bit less than 4. So what does it look like you're going to get to? 10, exactly. So the limit as x approaches 4 of 3x minus 2 is 10. The next one, the limit as x approaches 1 of 2x squared plus x minus 4. So as x approaches negative 1 here, again, my hand's in the way. As I approach negative 1 from this side and this side, what does it look like I'm going to get? Negative 3, yes. Now, on both of these, had I just substituted in this number, like if I'd have done 3 times 4 minus 2, I'll get 10. If I substitute negative 1 into here, I'll get negative 3. Okay? So let's substitute negative 3 into here. Negative 3 cubed is negative 27 plus 27 over, then that would be 9 minus 9. That gives me 0 over 0, which is undefined. But the limit is not undefined. Okay, this is why you cannot just go substituting in. There is a time and a place for that, and we'll talk about what that is a little bit later, but right now we're just going by the graphs. So let's look at this graph, and then we'll talk about why we get that when that's not the answer. So here's number 6. That's what your graph looks like. And we want to know what's happening as x approaches negative 3. So as x approaches negative 3, there you go. When I actually get to negative 3, it says undefined. I don't have an answer there. But it looks like if I go on either side of it, negative 4.5, would you say? On either side of 3, you can just click and drag back and forth. It's negative, so I'm going to just put an X through that, but leave that. It's negative 4.5 is my answer, not 0 over 0. So let's take this up here, and let's factor this. The numerator is a sum of cubes. That's something you should be able to factor quickly and accurately. Sum of cubes is going to give me a binomial and a trinomial. Your acronym for that is SOAP. The signs are the same, opposite, always positive. Since this is x cubed plus 27, this would be x and this would be 3. That would make this x squared, this 3x. and this 9. The denominator is a difference of squares, so this is going to give me x plus 3 times x minus 3. Can I simplify that? Yep, I can cancel those out. And when you have a rational function and you cancel out a factor, what ends up on your graph? A hole. This is a hole at x equals -3. That's why you get undefined when you actually go to -3, because there's a hole there. We good? All right, so let's look at number 7. We'll look at it as a graph. And your assignment, I have a Desmos that goes along with your assignment, so the graph's already there, so you don't have to type them all in. These are the slide numbers. These are the question numbers, so make sure you're on the right one, plus you can match up those easily. So here's your number 7. We want to know what happens as x approaches 0. So as x approaches 0, when I get to 0, it's undefined. But on either side of 0, when I get those numbers, what do you think I'm approaching? 0.5? 0.5. Okay. All right, so here we want to know what happens as x approaches 1. So when I get to 1, it's undefined, but by looking at the numbers on either side of 1, what do you think the answer is? 2. Yes. Okay. Then the limit as x approaches 3 here, so 3 is right about here. As x approaches 3, 3 is undefined, but what do you think the limit is? What do you think it is? -1. Right, any questions on how to find any of those? Easy enough? All right, so let's talk about when a limit can fail to exist. A limit can fail to exist under any of the following conditions. If the function contains a jump and therefore approaches a different number from the left side of C than from the right side of C. Now on the example 1, I don't think the graph copied very well on yours, so it looks like this. That's open, and this is closed. I don't know if you can even tell what the graph is, but that's what it looks like. So if I want the limit as x approaches 0, as I approach from the left, I'm approaching a -2. As I approach from the right, I'm approaching a +2. I actually make it to a +2 here. Ooh, I actually make it to a +2 here, but I'm approaching 2 different things. That's why it doesn't exist. You have to approach the same number for it to exist. Okay. The other time it can fail to exist is when it has a vertical asymptote and therefore increases or decreases without bound. So here is my vertical asymptote. As I come from the left, as x approaches -2, I'm approaching -infinity. As I approach -2 from the right, I'm approaching infinity. Doesn't exist. Okay. And the third time is when the function oscillates between 2 values. So the limit as x approaches 0. You can see that it's just bouncing back and forth as it gets closer and closer to 0, so it's not approaching anything because it's jumping back and forth. So that's it does not exist also. Okay, we good? All right, so now I want you to open your tablets, go to student.desmos.com, log in with Google using your district stuff. You should see 2 assignments there. One says notes, one says homework. Go to the one that says notes. Okay, student.desmos.com. And I've already gone through the first few with you, so I'm going to go to slide 8, which actually is number 10. It should look like this. So I want you to be able to click around and drag on your own as well. Are we there? No. All right, so while we're waiting on everything to load, let's go ahead and do 10 and 11 together. So on 10, we want the limit as x approaches -1. So here's -1. I'm approaching from the left, I get to 2. I approach from the right, I get to -3. So what's my answer? if I'm approaching two different things? Does not exist. So that's the answer to number 10, does not exist. Okay. We'll do 11 together also. So the limit as x approaches, and number 10 and 11 are both piecewise functions. The limit as x approaches 2, so you can tell you got the red and the blue because the two pieces meet here. But as x approaches 2, what does y approach? Bless you. 6. See how you're at 6? 2, 6. Okay. We good? All right, so I want you to do 12 and 13 using the graphs and the notes. Pardon Desmos. All right. So on number 12, I want to know what happens as x approaches 1. So as I click and drag here, as x approaches 1, it's undefined there. But what does it look like y is approaching? 0.1? Yeah? Good, 0.1. You can also, because I know y'all have some knowledge of Desmos, you can add a table and type things in if you need to, or let that give you a table, whatever works for you. All right, 13. So you can ignore these little vertical pieces because that's just what happens when you have an absolute value sometimes. I don't know why. But we want to see what happens as x approaches -1. So if you haven't done that one already, go ahead and see if you can figure that out. Are we approaching the same thing from the left and the right? No. If I'm coming from the left, I approach -1. If I'm coming from the right, I approach 1. So what's my answer? Does not exist. You have to approach the same value. But we weren't asking what happened at the asymptote. So there is an asymptote here. So if I had asked you what happens as x approaches -4, then that would be does not exist. But since I'm asking about something else, that's why. It's not just that it has an asymptote, it's that you're looking for the limit at the asymptote. That's a good question. Anything else? Okay. So let's look at 14, a trig one. This is the cosine of 1 over x. If we zoom in some, what's happening here? It's oscillating. Good. So it's oscillating. If I wanted the limit as x approaches pi-thirds, that's different. I can figure that out. But when I want the limit as x approaches 0, it's oscillating around 0. That's what makes that one does not exist. Okay. And go ahead and look at 15. The limit here is x approaches 0. What do you think about that one? Ooh, close. I think it'll tell you the exact answer, won't it? -pi4, yeah. You can actually get there. If you can get there, that's great. 0, it's -pi4. See, okay, see if you can make sense of 16 and 17. For 16, if I want the limit as x approaches pi halves, do you even really have to click and trace? I mean, there's pi halves right there. You can see that it's approaching 0 from either side. And then 17, the limit as x approaches pi halves. What's happening at pi halves on here? A vertical asymptote. Good. And this is approaching infinity. This is approaching negative infinity. Does not exist. Okay, we good? All right, here's a little side note about the vertical asymptotes and the unbounded behavior. So this says, in some cases, the left and right side are both increasing without bound or both decreasing without bound. So that means if you're increasing to infinity or decreasing to negative infinity, that's without bound because it goes on forever. So technically, by what we said earlier, this limit would not exist because if I want the limit as x approaches 0, there's a vertical asymptote there, and then it does not exist. But the better answer is does not exist, increases without bound, because it still tells you something about the graph. It's not just that, oh, it doesn't exist for any random number of reasons. So this does say, though the limit technically does not exist, instead of writing does not exist, increases without bound, it's acceptable to say infinity. The reason infinity technically isn't a right answer is because that's supposed to be a value, and infinity is not a number. It's not a value you can actually get. So I'm just giving you those specifics. We're going to use infinity and negative infinity, but the better explanation to that is does not exist, increases without bound. So if we look at number 18 here, I want to know what happens as x approaches 0. Since they're both going to negative infinity, then my answer can be negative infinity. And then if you look at 19, tell me what you think about 19. Infinity. Very good. All right, what questions do you have? Okay, so you should see, since you're in Desmos right now, that you have another assignment in there that says homework. And so those graphs will go along with this. You can zoom in, zoom out, add tables, do whatever you need, but they're already typed in, so you didn't have to do all that. I'm going to give you the piece of paper. My suggestion would be maybe go through and use Desmos and get all these done, and then go back and put them in formative. But 1, 2, and 3, and it even says so in formative, you have to do 1, 2, and 3 on your paper because you're writing it in limit notation. I don't want you to have to try and type that in. Okay, the stuff that you're typing in is easy, like numbers or does not exist or something like that, and then you'll know if you're right or wrong. Okay, we good? All right.